In this particular example, we're going to calculate the delta H of the following reaction. We have 2 carbon as a solid plus hydrogen gas is going to give us C2H2 as a gas. And we're given the following 3 reactions here. And this is going to be a direct application of Hess's law. And with this, we can manipulate the reactions and use the principles we learned from a previous video to calculate the delta H of this reaction. Remember that we can manipulate the delta H by switching around the order of a particular reaction, and we can also manipulate the delta H by the amount of a particular reactant and product that we have present. So when you're given a step of various reactions, one thing that I will give you as a hint is to kind of place a box around all the products and reactants to indicate where they are. So for example, here we have 2 carbon as a solid. Carbon shows up in the first reaction right here. Okay? Also as a reactant is hydrogen gas. So anytime hydrogen gas shows up, we also want to circle that. Okay? C2H2 is a product. So we're going to circle this one, and we have C2H2 down here as a product. Okay? So when we use Hess's law, we can add all of these up, and we can kind of switch them around and change around the coefficients, which will change around our energies, and hopefully when we add these up, we're going to get 2 reactants and 1 product. So first, let's look at the carbon. We have 2 carbon in our overall reaction, so we need to take 2 times reaction number 1. And if we do that, we're going to get 2 carbon solid plus 2 O2 gas, giving us 2 CO2 gas. The delta H for this reaction now is going to be 2 times negative 94.1 kilojoules. Okay? Because we took twice as much of reaction number 2, so we're going to get twice as much energy. For the next reaction, our reactant is hydrogen gas. And in the second reaction, we have 2 moles of hydrogen gas. So we're going to take a half times this second reaction. And when we do that, we're going to get 1 mole of hydrogen gas plus a half a mole of oxygen gas, giving us 1 mole of water. Our delta H now is going to equal 1/2 times negative 134.8 kilojoules. So now we need to look at the third reaction, which has C2H2. As it's written on this piece of paper, C2H2 is a reactant, but we need it to be a product. So we need to reverse reaction number 3, which will then flip the sign. So here we'll have 2 CO2 as a gas plus water in the gaseous form to give us C2H2 in the gaseous form plus 5/2 O2 also as a gas. Our delta H now for this particular reaction will be positive 311.1 kilojoules. So now we can add up all of the steps of these reactions, and that will give us an overall delta H of reaction, which we can use because this is a state function. And what we're going to find is that some of our products and reactants are going to cancel out. So for example, when we add these 2 reactions together, we can see that there are 2 moles of CO2 as a reactant and as a product. So we can cancel those out on each side. Okay? So when we can kind of put these together, we can also see that the water will cancel out. And here we have 2 plus a half, or 4 halves plus a half, or 5 halves O2 on the left-hand side, and we also have 5 halves O2 down here on the right. So each of these oxygens are going to cancel out. So when we add all three of these reactions together, we get 2 carbon solid plus hydrogen gas, giving us C2H2 as a gas. And now we can add up the sum of all of these delta H values to get the delta H of the overall reaction. So we have 2 times negative 94.1 plus a half times negative 134.8 plus 311.1. This is going to give us a value of positive 55.5 kilojoules, which indicates that this particular reaction is going to be an endothermic reaction. So by using Hess's law, we can take a multi-step process and look at our overall reaction, and if we're given the delta H's of each individual reaction, we can then determine the delta H of the overall reaction. And we'll go over one more example of Hess's law in the next video.